Right. And it seems to be recording. Okay. All those things. So let me say first that this is a really important thing to mathematicians. It's a really big idea for them, and it keeps turning up, even in calculus. There will be times through the use of calculus especially for science and engineering, where this idea is going to turn up in disguise. And also, it's sort of like the first thing that you learn that's really abstract in a maths abstract way. And that's one of the reasons why people can find it a bit hard, because it's of a whole different character from the other stuff that you've learned in the past. You just end up, you feel like it's not like the maths you've seen before. And a lot of people, when they study this, go, oh, I thought I was okay and good at maths, and now I feel crap. So lots of people feel that way. And yeah, those are important feelings to recognize. And there's reasons you feel that way. And it's to do with the fact that this is a different sort of thing. Mathematics has a whole lot of different facets. And a lot of the things that are going on here are about the fact that this part of the course, this area of study, is all about the definitions and the theorems. It's all about what is true and what's not true, and you being able to connect that information together to solve problems that you've never seen before, and to be able to make new truths. So that's different to what you've seen before. Like in many ways, it's much closer to, say, circle theorems or like parallel line geometry sort of stuff than it is to calculus. Yeah, but that's what algebra is about. So when a mathematician says algebra, they mean the connection between ideas to do with calculating. Okay, just want to reassure you that yeah, it's okay to feel that way, and it's actually important to feel that way, and to recognize that you feel that way. Okay, so this is about ideas. This is about big ideas that go together and how they're related to each other. And one of the big ideas is that there is such a thing as a vector. But even before that, that there are both points and vectors. So I'm just going to mention that first. All right, so the first thing I need to say is that to a mathematician, vectors and points are the same thing. So, I mean, not quite, not always exactly the same, but to a mathematician, when they say vector, a large amount of the time, they mean point. Okay, so when you see something like 5, 6, 8, 0, -7, you know, it's got like 5 coordinates. At the moment it's written, it's a point in 7-dimensional space, and the 7-dimensional just means that it has 7 coordinates to tell you where it is. And these coordinates could represent anything. It could be the length and the width and the height and the temperature and how far round the wheels are of a bicycle. It doesn't have to be physical distances. They can be all sorts of different measurements, and that's why you're allowed to have 7 dimensions, because many objects have multiple ways of measuring. So this is a point, and when it's just sitting there like that, it's a point, and I think of it as a dot somewhere in space. And when I think about a set of things and say, well, all the ones where the x coordinate plus the y coordinate equals 12, that's a collection of dots, and I color all the dots in, and together they are the set. So when I think about them as just the coordinates like this, then they're a point. Okay? But when I think about adding them and multiplying by scalars, then I think of them as arrows, 5 of. Then I think of them as arrows, because it's easier to think about multiplying this by 5 by thinking of it as an arrow and making it 5 times longer. But to a mathematician, all of this is vectors. A mathematician doesn't think that a dot and an arrow are fundamentally different. They're just different ways of drawing the same idea. Okay, so over in physics, numbers, like there's vectors and there's scalars, but for a mathematician, vectors are just things that you can do addition and scalar multiplication on. So just really important thing. Next thing I want to talk about is sets. So a set is any collection of things of any kind that has a rule for telling whether you're in or out. And mathematicians write sets usually using curly brackets. And the reason why I'm talking about this now is it's so important to what subspaces are, because subspaces are a special kind of set. Now, everything is a set. Anything that you can think of, any drawing that you can make on the piece of paper is a set in R2. Everything is a set. And a subset is just a smaller set inside a bigger set. Okay. So that's all subset means. The word sub is designed in maths. It's not word, but the prefix sub in maths is used to say a thing inside another thing. It's a little bit like a suburb. Urb means city. A suburb is a city inside a city. So a sub set is a set inside a set. A subspace is a space inside a space. Okay, so sets have to have a rule for telling whether you're in them or not in them. And as long as there's a rule that's unambiguous, it counts as a set. And most of the time when we draw them, we just color in all the points that are in the set. So when we're thinking of sets, then we're thinking of our vectors as points. So when we think of a set in R2, then we could color it in. And all of these dots, they are the vectors. I'm not thinking of them as arrows, I'm thinking of them as dots. Okay, that's the idea of a set. So R2 is all of this, and this is the subset here. Okay, so there are three ways to define a set. So one way is to draw curly brackets and just write a list. Okay, and so that's the first. Actually, I need more space than that. Just a second. All right. So there are three ways to define a set. So the first way to define a set is to write a list. You curly brackets and you put a list. So for example, you might have the set of 0, 1, and 1, 0. Or you might have the set of just the 0 vector. Those are ones where you define it using a list. And the rule for deciding if you're in this set is if it's in the list, it's in the set, and if it's not in the list, it's not in the set. Okay? So the rule is in the list is the same as in the set. Not in list, not in set. Okay, that's important, and it seems like a stupid thing to say, but It's not. Okay, anytime you see something written like this, that is the totality of everything that is in that set. And they are dots, points. The second one is sort of a shortcut way of writing a list, but your list might have infinitely many things in it. So what you're going to have is you're going to have something like a way to construct something and then some technical details. Okay, and this thing is called such that when you read it aloud. So for example, the set of a, b plus 1, no, maybe not. Set of a squared such that a is in R. So we've got this construction. Here we construct a point with these coordinates, and then I tell you some technical details about what the letters here mean and what options there are for what those letters could stand for. And so this rule is that I can tell if something is in this set if it can be rewritten in this format. You can also see them like this. Something like that is a classic. The set of S103 plus T times 587 such that S and T are in R. Here's a thing to construct. You do this calculation, and as long as you do it for any real numbers S and T, then that is something in the set. So the rule is if you can write it this way, then it's in the set. And if you can't write it that way, like if nobody can write it that way, then it's not in the set. All right, and then the last way of constructing a set is to have, some sort of type of object such that a rule to satisfy. So this would be something like x, y, z such that x minus 3y plus z equals 4. So, and normally you'd say x, y, z like in R3, something like that. So this is the kind of object, these points, and it's in the set exactly when it works in this rule or not doesn't, and not when it doesn't. So the rule is in the set when it satisfies the rule. Those are the three ways of defining a set. And it's so important because everything else that comes after this is based on this. And there are some classic Maple TA questions that are used in this course where you get given a list of things that are written in these notations and you're supposed to decide if they're subspaces or not. But before you can even decide if it's a subspace, you need to know what the rule is for telling if something's in the set or not. So these things only have a few dots in them. These things could be all sorts of ways of constructing things, and this is the other way around. So I just want to show you something that's different about these, compare them, because anytime you see a maths thing or anything in any course, it's important to sort of stop and think, how are they similar, how are they different? So that you can tell what might be important about them and how to tell the difference between them. So what's different about these compared to that is that these ones list the exact things that are in the set, whereas these ones don't. These ones, you're going to have to figure that part out yourself, okay? And these ones are able to have infinitely many things in them, whereas these ones not so much. Sometimes you do these with dots, and so like, dot, 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 and that's fine as well. So the main difference between these two is that in this one, it tells you how to find all of the things in the set. In this one, it says, if you do this calculation and you use all the possible values of A, that will give you everything that's in the set. This is a full description of the entire everything. The problem with this one is it's not very easy to tell if something's in the set. If I just gave you a random vector like 1, 5, 8, it would be very difficult to tell if it would be possible to rewrite in this format. That's hard to do. But like, you can make things in this set as often as you want. You just pick different numbers for S&T, do the calculation, and there it is. So this one's easy to find things in the set, but hard to tell if a random thing is in the set or not. This one's the other way around. It's got a rule. If you just get given a random vector like 187, you can just sub it into the formula and see if it comes out to 4. And if it does, then it's in the set. And if it doesn't, then it's not. So this one, it's easy to tell whether a random thing is in the set, but it's very hard to just tell someone something that is in the set. If I asked you to say, tell me a vector that's in this set, you would have to think of something that does satisfy this rule. And it would be not as easy as it would for this to do that. So this one's easy for deciding if things are in the set, and this one's easy for making things in the set. And that's one of the big ideas that subspaces, everything that happens in subspaces is built on. Okay, I'm just going to pause for a moment. Does anyone have anything they'd like to say or comment on at that point? Feel free to use the chat. Or to talk.
I was just wondering, in that third type, what does it say at the very bottom for the rule?
Oh, yeah. That's my, that's why I'm so good at teaching medical students, because my handwriting's awful. It's in the set when it satisfies the rule. Like this rule, the rule that's stated.
Yeah, thank you. I was just also wondering, what does the straight line mean again?
Most people pronounce it as such that.
Yeah, thank you.
Some people write it as a colon. Stuff here, stuff there, and then the 2 dots, a colon. Different lecturers, different mathematicians have different opinions about which one to use. You're allowed to use whichever one you like. I find the colon looks, it's easy to lose if you're handwriting. It's sometimes hard to tell whether it's there or not.
David, with the first one,
yep, the list.
Yeah, is that just like to be in the set, you just have to be one of those points?
Yep, exactly.
Okay, all right.
Yep. If you're not in the list of points, you're not in the set. If you are in the list of points, you are in the set. It's just a literal list of everything that's in the set.
Yep, I got you.
So that's good. This one here specifically contains exactly 1 point.
Yeah, so you have to be that point there to be in the set. You can't be anything else.
Yep, and if you're not at that point, then you're not in the set.
Yeah.
Those are some really good questions to get a handle on how this works.
Sorry, they're all different ways of writing subspaces, right?
Yeah, but they're ways of writing. It's bigger than that. Subspaces can be written these ways, but things that aren't subspaces can be written this ways as well.
Oh, okay.
So let me just show you one. So this one here, for example. That was a very excellent question, actually. I don't know who was talking then. I'm sorry. It's a bit hard to keep track of all of this when I've got sharing something on the screen. So I have to have things where I've got an A, like 1, and then 1 squared. So that would be the point 1, 1 squared. And then 2, 2 squared would be here. And 0, 0 squared would be here. And like 1.5 squared. So what happens when you do this is that when you collect together all of those points, this forms this parabola. That's the drawing of this set. So this is a description of the graph of y equals x squared. And that's not a subspace. It's just a set. Does that help to clarify what I meant?
So why is that not a subspace then? Because
Yep.
yeah.
Yep. What were you going to say?
Oh, sorry. That it had. Well, it's still a collection of points. If
Yep.
if you had all little dots along every point.
Yep.
Of that graph, then
That's a really important question, and I'm going to answer that now. Is that okay? Okay. Okay. So this is a subset of R2. It's not a subspace of R2. So now I'm going to tell you what a subspace is. So a subset is anything at all. If you can think of a rule or draw a picture and think of a rule that decides what's in and what's out, even if that rule is just, it's the things in this drawing, then that's a subset. But only some subsets, only some of them are subspaces. And subspaces are a very special kind of subset. They are a subset that you can't escape by doing the things that vectors do. Now, that's not a maths definition, so I'm going to put inverted commas. Now, that's a very vague thing to say. You can't escape by doing vector things. So I'll clarify what I mean by that. The thing that vectors do that to a mathematician makes them vectors is being able to add them and multiply them by numbers. I've got a question there, how this all look in matrix form. We're going to get to that soon. Okay. Okay. So vectors do this thing. Vectors do addition. I can add vectors, just add the matching coordinates and ta-da, and they do scalar multiplication. So the official name for just a number is a scalar. But that's fine. So they do addition and scalar multiplication. So just you can multiply them by numbers. And in order to do those operations, I have to think of them as arrows, like put the arrows head to tail and whatever. But I can also just do it with the rules. Multiply by 5 means multiply each of the individual things by 5. That's what vectors do. And to a mathematician, that's what a vector is. A vector is a collection of vectors. A vector space is a collection of things that do this. Okay, so those are the things that make something vectors. So a subspace is a set that you can't escape from by doing the things that vectors do. That's why this is not a subspace. Because when I take, say, this point and say this point, and I go, what would happen if I added those 2 points together? So to add them, I would have to think of them as arrows and put the arrows head to tail, and the sum would end up here. And I was able to escape this curve by adding those 2 dots together. So it's not a subspace because I was able to escape it by doing addition, which is the thing that vectors do. So whoever asked me that question before, does that give you a little bit of clarity?
Yeah, it makes some sense. I don't think they I can't remember in the lectures if they made the distinction between subsets and subspaces.
Yeah, well, they probably
did.
They probably didn't explicitly say it aloud. Yeah.
Okay. Well, thank you.
Yeah. Because they just use the word subset all the time and then only use the word subspace in some situations. So you might not have noticed the difference. That's normal. Yeah, but though I wish they had been more explicit about it. Okay.
Just a quick question. When you think of a subspace, do you think of them as arrows?
You think of them as arrows when you're doing the operation, but the subspace itself is a set of coloured in dots.
Yeah. All right. Thank you.
So the subspace is the region that you can't escape, and the actions that you're doing to try and escape it, that's when you're using arrows.
Yes, gotcha.
Okay. Everyone's got on fire with the good questions today. Okay, so just can I squeeze something in here before I go further with the subspaces? Jordan, you asked, what does this look like in matrix form? I just wanted to show you, matrices tend to fit into this type of object such that rule setting. So I'm just going to just do one more example of that. X, Y, Z in R3 such that 1, 0, 2, 0, minus 1, 5 times X, Y, Z is 0, 0. That, for example, is a matrix way of writing a set in this format. X, Y, Z, the set is made of things in R3, but only the ones such that when you multiply them by this matrix, you get 0, 0. And that's a perfectly good rule for deciding whether a point is in a set or not, to do a matrix multiplication and see what happens. This will come back in a minute, so just bear with me. I just wanted to say it now. Okay. So we were in the middle of talking about subspaces. I still don't have an official maths definition for this. I've just said, well, you can't escape by doing the thing that vectors do. And so I need a proper maths definition. So the maths definition has 3 parts, and one of them is to do with the addition, the other one's to do with the scalar multiplication, and the other part is just to make sure that it has vectors in it at all. Because that would be silly if it was empty, if there was no vectors at all, and say, this is my set, it doesn't have any vectors. And that's the secret 0 type of vector of subset, is one that doesn't have anything in it at all. The rule for being in the set is that nothing's in the set. That's called the empty set, and a subspace isn't allowed to be empty, because otherwise, well, how are you going to try and escape it if there's nothing in it at all? So anyway, so rule number 1, so these are the definition. W is a subspace of Rn when, rule number 0, I call it, the 0 vector, I've underlined it, in the textbook it would be written in bold, is in, that's how you pronounce this symbol, W. Okay, so it has to contain the 0 vector, but that's not the only rule. This is just to guarantee that something is in the subspace at all. Rule number 1, if the vector V is in the subspace, let's call it W, is in the set, then KV has to be in the set too for any K in R. Okay, if you have a vector, which means a point in the set, then when you multiply that vector by a scalar, so you extend the arrow and look at what that point becomes, that new point has to be in the set as well. And if that doesn't happen, then it's not a subspace. And number 2, if W and V are in big W, then W plus V is also in big W. So if you have 2 things that are in there, and then you find those points and you add them together and find what that new point is, if that new point isn't in there anymore, not a subspace. But if every time you pick 2 things and you add them together, every time you end up in the subspace again, like in the set again, then the set is a subspace. Those are the 3 rules. I call them rule number 0, rule number 1, and rule number 2, because this one is about the 0 vector. This one uses 1 vector and this one uses 2 vectors. But you don't have to number them. This is called the, they have names. It's the 0 rule, the scalar multiplication rule, and the addition rule. And they call these things, so rule number 2, rule number 1 is called closed under scalar multiplication. The idea being that the door is closed, you can't escape. And rule number 2 is called closed under addition. So they call it a subspace for a reason. it's a space inside a bigger space. The reason it's called a subspace is because when you're looking at your subspace and you sort of cut it out and take it out of R2 or R3 or wherever it is and look at it all by itself, then the vectors will still do the things that vectors do independently of the rest of space. If my 3D space, here was R3 and my table was R2, drawings on the table don't interact with the rest of space. I can just have the table all by itself and it will be fine. And that's the idea of a subspace. It acts like a space all on its own. So the table behaves as if it was R2, even though it's made of vectors that are in R3. Okay, that's the idea of a subspace. That's the definition of a subspace. So if it doesn't contain the zero vector, not a subspace. If at any point you have a point in it that when you multiply it by a scalar, it's not in there anymore, not a subspace. If at any moment you have two things when you add them, then the result isn't in there anymore, not a subspace. And there are many, 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 many non-subspaces. Okay, most of the things that you randomly draw are not subspaces. This first set that I drew is not a subspace. Because, for example, if I have this point and I take it as an arrow and multiply it by 2, then I've escaped. So it's not a subspace anymore. It was never a subspace. It wasn't closed under scalar multiplication, so it's not a subspace. Okay. So it is useful. So here is a thing that you need to know about the way definitions work. Mathematicians think that definitions are the thing. Definition is what the thing is. They've spent a lot of time coming up with a definition that is useful and is a useful way of characterizing all the information you need to know about this object. But they forget that human beings, mathematicians are human beings too, but they forget that human beings do not understand things by definition. You don't know what a dog is because someone gave you a definition of a dog. You know what a dog is because you've seen lots of dogs. And so when you're given a definition in a maths class, if your lecturer doesn't give you a lot of examples of things that are and things that aren't, so that you can get a feel for what it looks like and what it feels like, you're going to need to find them yourself. And they are there in your lecture notes. They're just hidden because they might not be listed as example. And so I'm going to tell you some things that are and some things that aren't, so that you don't have to check the rules. There are going to be times when people are going to ask you to prove that something's a subspace or prove that something isn't, and then you're going to have to come back to the rules to make the definitive final choice. But it's nice to know what sorts of things you expect to be subspaces and don't based on the way that they're written. So that's what I'm going to do. Before I move on, questions or thoughts at the moment?
Sorry, quickly. Seeing you said that was adding two points in the subspace.
Yep.
That has to be in the subspace as well.
Mm-hmm.
Would that, in a way, geometrically, would that look like that a subspace would have to be whatchamacallits? Symmetric around the line y equals x?
No, maybe. I'm not sure what you're getting at. I have a feeling that I know what you're getting at. Are you saying that it should have to contain both sides like that? Or are you saying that it would have to be that way symmetric?
Yeah, it has to be symmetric around. That way.
Yeah. Yes, a subspace will have to do that. And that works from the scalar multiplication rule as well. If you multiply something by -1, it has to be in there too. So this can't be a subspace, because if it was, this bit would be down here too. Yeah, but it's also not a subspace for a whole lot of other reasons. So I'm going to get to that. Okay, but that's some good instinct there, actually. So if you know that a specific point is in the subspace, then because of the scalar multiplication rule, so let's just some consequences of this. If I said to you, I'm thinking of a subspace and it has this point in it, then you would know that if I was thinking of a subspace that contained this point, then you would know that it also has 0, because it's always got the 0 vector, and it also has half of this, which is there, and it also has 2 of this, which is there, and it also has minus this, which is there, and it also has minus 3/4 of it, which is here, and it also has 10 of it, which is over here. And in fact, if that black point is part of my subspace, then this entire line will have to be part of the subspace too. Okay, so that's one thing about subspaces. If any one point is in there, then the whole line through the origin that contains that point must be in the subspace too because of the scalar multiplication rule. What that means is that subspaces have to be made up of lines. Yeah. And the addition rule tells you that if I have two things that are in the subspace, then when I add them, this arrow plus that arrow, then this has to be in the subspace too. And when I add them, when I add like this one to, since I can add anything, I could add this to that one as well. So this would be in the subspace too. And I can add this to that one and I can get this, and you get this entire grid of things that must be in the subspace. And even better, because I know that this entire line has to be in it and this entire line has to be in it, and anything on this plus anything on this has to be in it, what happens is that the whole plane ends up being in the subspace too. So the only way that you can have a subspace with two separate points in it like that is for the entire plane to be part of the subspace too. Now that happens in 3D as well. If I had two things like this, then this whole line would and this whole line would, and so I get this plane that's not flat, like not horizontal, that has to be in there as well. And that's sort of what happens. So subspaces tend to always have to look like lines or planes or sort of flat things. You can fill out the whole of space as well. So that's just a useful thing about how they have to look. So 2 points mean that the whole plane. Okay. Cool. Of course, this doesn't work if all you have is the origin, just that dot, then that doesn't force any lines to be part of it because, you know, when I multiply it by stuff, it doesn't go anywhere. So the origin by itself counts as a subspace because you can't escape it by doing these operations. Right. Cool. So this is telling me that subspaces, when I think of what the picture looks like, they have to be lines or planes or flat things, three spaces, that sort of thing. And that's a good start, which is why I know that this can't be a subspace. It's the wrong shape. If it was a subspace, it would be a line. And since it has two separate points, if this was a subspace, it would have to contain everything, and it doesn't. It's only got these points. All right. Where are we up to? 12. Got about half an hour. So there are some things. I'm going to look at these three different ways of writing a subspace. And what we're going to do is we're going to say what way of writing guarantees that it must be a subspace without having to do any of the proofs. Okay? So if you have a list way of writing things, the only list that is a subspace is this one. That's the only one. And the reason for that is that this, no, further, even further, this can't be a subspace. Because if it was a subspace, then it would also have 0, 2 and 0, 7 and 1, 1 and all the operations I could do on these. And those operations I can do aren't part of this list. And so they're not in the subset. So this set here is not a subspace because it doesn't contain all the things it should contain. It's only got these 2 points. But if all you have is the origin, oh, sorry. I'm breaking out, am I? I'm hoping that I did repeat it after all. If you have more than 1 point in this list, then it can't be a subspace because only the points in the list are done. And once you've got a couple of them, then there have to be infinitely many other choices as well. But just the origin, definitely a subspace. This is the only subspace that's writable as a list. All right. The construction, anything that looks like this. You know, S times vector plus T times vector such that S and T are in R. Always a subspace. And in fact, if you can rewrite your thing here to look like that, it's a subspace. But the important thing is you have to use all the real numbers. The reason this is a subspace is because these are, say, my 2 points that I've picked. And I know that any scalar multiple of either of them is in the subspace. And I know that when I add anything together that's already there, it's in the subspace. So what I've done is I've just included all the possible things that I could possibly calculate. And so it's sort of by default has to be a subspace because I've just included everything that I could possibly include. This thing is called a span. So the idea of span is that when I take some vectors and I make all the possible additions and scalar multiplications that I can possibly do with them, and I get all of those points together they are called the span of those vectors. And a span is always a subspace. I believe there's actually a theorem in your notes that says that. So it doesn't have to be like this. It could be like A1 V1 plus A2 V2 plus A3 V3, etc. There could be as many of them as you want. And these A's are all real numbers. This is called the span of V1 up to whatever however many there are. That's what span is. So the list one, the only subspace that is, sorry, someone's just asked me if you can't see the chat. Someone's just asked me to repeat this. The only subspace that is writable as a list is a list that just contains the 0 vector. Any other list at all, like this with 2 vectors or something with 4 vectors or something with 5 vectors or something with 1 vector that isn't the 0 vector, all of those, none of them are subspaces. The only one that's a subspace is this one. And the reason they're not is because you can always think of some sort of scalar multiplication or addition that will be something that's not in the list. Except for this, because any addition of that by itself will still be 0, and any scalar multiplication will still be 0. Now, someone has also asked, Karen, thank you, why is this always a subspace? So the airy-fairy reason is it's always a subspace because I have just literally listed all possible additions and all possible scalar multiplications. So if you've included all of the possibilities for doing additions and scalar multiplications, then it must be impossible to escape because I've included them all. That's the reasoning reason. The proof reason, I can talk about that in a minute as well. I will do a proof if that's okay. But first I want to finish this page. So the last one, which is the one with the rule, if your rule is, you know, you've got vectors, you know, just some sort of vector such that a linear equations homogeneous linear equations, this is always a subspace. So this one that I drew before, just here, that is a linear equation and it's not homogeneous, not a subspace. But if this had been a 0, then it would have been a subspace. So for example, x, y, z such that x minus y plus 3z is 0. A subspace definitely, because this is a linear equation that's equal to 0. These are the things that are definitely always subspaces. So we have this and the pictures. If it's a straight line through the origin, definitely subspace. Plane through the origin, definitely subspace. All the subspaces have to look like that. If it's a list, well, the only way it can be a subspace if it's a list if it's just the 0 vector. If it's a construction, there are other ways to do this, but if it's a span, if it's something that's all the linear combinations of things, then it's a subspace. But if there's even one combination missing, it's not a subspace. So let me just do some examples. So for example, S 3, 5, 7 plus 1, 0, 8 such that S is in R. This one is not a subspace. And the reason it's not a subspace is because I haven't included all the combinations. I've got any scalar multiplication of the 357, but I'm not allowed to do any scalar multiplication of the 108. I'm only allowed to have one of the 108. That's telling me that this is not a subspace. Now, you in your exam telling someone that that's the reason it's not a subspace wouldn't be acceptable, but it would definitely allow you to answer a multiple choice question of whether this is a subspace or not. You can look at it and go, nah, not all the combinations are included. It's not a subspace. You're right. Now, if you wanted to prove definitively that it's not a subspace, you would have to show that there were some things in it that when you multiply them by scalars or add them or something, aren't in it anymore. And that's actually going to be quite hard for this one, and I'm actually going to give it a go. So I know, for example, that 108 is in this subspace. Let's call it W. Sorry, it's not a subspace. Is in this subset. Because what I've done is I've chosen the S to be 0. And I'm pretty sure that if I multiply this by 2, it's not going to be in the subset anymore. So let's see. If it was in the subset, then it would be like this. Like that. And then if I took off the 108, that would be 108 on both sides. Took off 108 here and took off 108 here. This is not a multiple of that. There is going to be no S that I can multiply this by to produce that those numbers. sure, I could multiply the s. The s could be a third, and that would multiply this 3 to give me a 1. But then the 5 wouldn't become a 0. And the only way I could get a 0 in this spot is to make the s 0. And the only way I could get an 8 in this spot is to make the s 8/7. Since it can't be all three of them at once, there is no solution. So 2, 0, 16 is not in W. So therefore W isn't closed under scalar multiplication, because when I multiplied this one by 2, it wasn't in there anymore. In fact, anything, this is a straight line. In fact, it starts at the point 108 and it goes off in the direction 357. Any straight line that is not through the origin will break the scalar multiplication and the addition rule as well. So even though straight lines through the origin are definitely always subspaces, straight lines not through the origin are never ever subspaces, and they break all the rules of subspaces all the time. I could have shown that the 0 vector isn't part of this actually, and that would have done the trick of not being a subspace too, but this argument was a little easier to do.
Sorry, David, what does that just say underneath the 2016 there?
Not closed under scalar multiplication.
Thank you.
Oh, and just a quick question, what is it under the first one? Not all...
Not all combinations, it's combos.
Yeah.
Not all combinations included.
Yeah, thank you.
So this is the one that's sort of in my head. Not all combinations are included because I didn't have a number in this spot here. But that wouldn't be my reasoning if someone asked me for a reason in an exam, because it's not specific enough as to exactly which combinations are missing that I'm thinking of. This one is saying, well, the specific combination of 2 of that's missing. But I knew to try for this because it looked a certain way. Yeah. X, Y, Z in R3. Oh, actually, let me just do. Excuse me. So this one, X, Y, Z in Z3, such that X plus Y minus Z is 0, is not a subspace of R3 because it would only be a subspace of R3 if it included all of the possible coordinates that satisfy this. And I've only included the ones with whole number coordinates. And so it doesn't include all the solutions to this homogeneous linear equation. And so I should probably, has to be in Rn, or it's not a subspace of Rn. It is technically possible to talk about subspaces of Z3, but it's just weird ass. No, don't go there. You may, if you study a 3rd year maths, pure maths course called Rings and Modules, you'll see that there. Pardon me. Okay, so now that's quite rare. That's a very contrived answer. This one, x squared plus y equals 0. I'm pretty sure it's not a subspace because this isn't a linear equation. Now, there are some subspaces that have quadratic equations. Just be aware. It's like this double bluff. This one, for example, x, y, z such that x squared plus y squared is 0. The only way that could the only way to satisfy this equation is for both x and y to be 0 at the same time. And so this is the same thing as x, y, z such that x equals 0 and y equals 0. And these are both linear, homogeneous linear equations. So it's a subspace. There's a lot going on there. But this is all to try and get you a feel for what the equations, what the symbols on the page will look like when it's a subspace and when it's not. All subspaces can be rewritten to have homogeneous linear equations, possibly more than one, and all subspaces can be rewritten to be spans. And so if the thing that you have has not linear equations or not spans, then it's not a subspace. And so if someone asked you, prove this is a subspace, or give an example that shows it's not, then a good thing to look is to see, well, is the equation linear? And if it is, then you'll try to prove it's a subspace because you know it is. The rule notation is a subspace when it's homogeneous linear equations. When the rule is homogeneous. Homogeneous means equals to 0. Linear means you're not allowed to have any squares or any of that stuff. Does that answer your question?
Yeah, it does. Thanks.
Ah, the integer one. Well, let's do a proof. Yep, I said this wasn't a subspace. Okay, well, let's do this one. So from the previous page, and we had this one, x, y, z in Z3 such that x plus y minus z is 0. I'm going to show that it's not a subspace. So it is definitely contains a 0 vector because 0 plus 0 minus 0 is 0. So the 0 vector satisfies it. So it doesn't break the 0 vector rule. So it's got to break one of the other rules. I think it breaks the scalar multiplication rule. That's always a good thing to try because it only needs one vector. So let's see. In order to break the scalar multiplication rule, I need to first find a vector that's in this set. So let me just think of one. What if I had 1, 0, and 1 for Z? 1, 0, 1 is in W. Since 1 plus 0 minus 1 is 0. Okay, it satisfies the rule, therefore it's in the set. Okay, and I want to do a scalar multiple of this that isn't in the set anymore. Now, 202 would still satisfy the equation, and 10, 0, 10 would still satisfy the equation, and minus 1, 0, minus 1 would still satisfy the equation. But what about a half of this? It still satisfies the equation, but it doesn't satisfy this. Is not in W since it's not in Z3. Because its coordinates aren't integers, it can't be part of this set. Yes. Katie's saying you forgot you could multiply by non-integers. That is an important beware of the toast moment. Beware of the toast means be careful of patterns that aren't really there. As in the classic game where you ask people to say words like most and ghost and roast, and then ask them what do you put in a toaster, and the answer is bread. So beware of the toast means beware of patterns that you form naturally. As a good human, you're good at forming patterns. Most of the examples that you see in this subspace thing use whole numbers because they're easier, but they're allowed to be not whole numbers. Fractions are allowed, and And so are irrational numbers like √2 and pi if you really want. It's just that it's hard to tell what's really going on when you do that. So very important point to have brought up, actually. Well done, Katie. Make sure that you consider fractional options sometimes. The integer ones are easier to think about, but it's important to consider the fractional ones too. Okay, so how are people feeling about knowing whether something's a subspace or not from the way we just, yeah, or whatever?
Feeling good, David.
Mm.
Good.
So you might remember there usually is each semester a Maple TA question with like 6 or 7 of these types of things with a set notation to say, are they subspaces or not? Was that here this semester? No, sorry, Mobius. It used to be called Maple TA. Sorry, they changed the name of the software. There was a Mobius question that had a list of things. Was that there?
Yeah.
Yeah. Okay, so this is the thing. And in the physical drop-in center, I usually get like multiple different students to get together, and we look at all of the options in everybody's Mobius and try to figure out what's similar and what's different, so that people can come to an understanding of this. It's quite fun, actually. Not on the day the assignment's due, that's just stressful, but but yeah. Just a second, I've had a knock at the door. I'll be back in a sec. I'm back, and someone was just going to ask something.
I was going to ask something about if the rule is like, let's say x, y, like the product. Would that?
Oh, yes. Good one. Something like that?
Yeah.
X times y equals 0. What do you think?
Not sure, to be honest.
Well, it's not a linear equation, because linear equations don't have any of the terms multiplied by each other. They only have addition and scalar multiplication.
Oh.
So this is not linear. So my expectation is that this is not a subspace.
Yeah. Essentially, just a general rule of thumb would be like, if it's linear, it will probably be a subspace.
Well, if it's linear and it's equal to 0, it is definitely a subspace. And if it's anything else, it's not.
Yeah.
So I'm going to prove that this one isn't a subspace. So the 0 vector works because 0 times 0 is 0. So that's not the problem. And actually, this one is going to always satisfy the scalar multiplication rule. Interestingly, so the scalar multiplication is going to be closed, because if I had something where they times to give 0, if I multiply them by say 4, they're still going to times to give 0, because one of them has to be 0 to do that. So it's actually the addition rule that breaks here, but that means I'm going to have to think of 2 things that are in the set. So let's see, 1, 0, 0 is in this set. Let's call it S, since the x coordinate times the y coordinate is 0. And 0, 1, 0 is in the set, since the x coordinate times the y coordinate is 0. But when I add them, I get 1, 1, 0, which is not in the set, since x times y is not 0. So it's not a subspace. But I knew to go looking for that because it wasn't a linear equation. So there was no point trying to prove it was a subspace, because it's not.
Yeah.
Yeah. Okay, so the last thing to do, if I'm going to talk about subspaces in my last 10, I might go a little over time, but I will have to eat lunch at some point. The last thing to do is to do a proof that something's a subspace, just so you can see how that goes, because that was one of the questions that was asked right at the beginning of how do I do that? I need to have a drink too because my voice is running out. Okay, so I'm just going to, proving. So I didn't get up to basis, I'm sorry, but I will say one thing about basis just before I do this proof. One thing about basis, you know how I said that every subspace can be rewritten if you want? Like, let me just go back to this. Here it is. So I know that the construction format, if it's written as a span or can be rewritten as a span, then it's definitely a subspace. In fact, if you do have a subspace, then it's always possible to write it as a span. Even if it's written like this at the moment, you can rewrite it so that it's written as a span. And when you rewrite it as a span, then the vectors that go in this position, that's the basis. The idea of a basis is what goes in this spot in order to make your subspace as a span instead of whatever way it was made originally. That's what a basis is for. So the point of a basis, point has multiple meanings here. The idea of a basis is that you have your subspace, rewrite subspace as the span of something. And then this thing, that's the basis. That's what a basis is for, to figure out what goes in that spot. The thing is that what you want is the shortest possible list of things to go in that spot, and that's a proper basis. If it's just anything, it's a spanning set, but you really want the fewest vectors you can. And the way that you guarantee that it has the fewest vectors is for them to be linearly independent, which I haven't defined today, but that's another story. I should say to you that there are multiple past revision seminars on the Maths Learning Centre webpage for Maths 1A that you can look up to find more stuff about this. Unfortunately, our website has been rewritten by someone else this year, and they've removed some of the important information. So it's just links to videos right now, but I have put them in roughly the order I think you should watch them in under each topic. So if you want to find more about basis, then go and check that out. Okay, so proving. I'll just say, any thoughts or questions about what I've said so far before I do a proof? All right, I'm going to assume that that's no. All right. Proving. And I'm just going to do an example. Prove that S, which is going to be equal to X, Y, Z, such that X minus Y equals 0 and Z plus 3X minus Y plus Y equals 0 is a subspace of R3. Okay. I have two ways to go about doing this. I'm going to show you both because I think they illustrate things. If you've got an exam where you have to write things, I wouldn't do both, just do one. Okay. They're very similar, but I just think that one's more abstract than the other. So let's see. My first way is this. I have to prove that it's a subspace. When a mathematician says prove, they mean you have to use a definition or a theorem. Now, there is a theorem. There is a theorem that says any subspace which is the solutions to homogeneous linear equations, it's not subspace. Any set which is all the solutions to homogeneous linear equations is subspace, which this is. This is a homogeneous linear equation. This is a homogeneous linear equation. It has to be the solutions to both simultaneously. That's what the comma means here. It means and. If it had said the word or, that it would have been different and it wouldn't be a subspace. I know this is a subspace because of that. But because they asked me to prove it, I think just referencing a theorem is probably not good enough. So they want me to use the definition. So the definition is that it has to have the zero vector, it has to be closed under scalar multiplication, and it has to be closed under addition. And so I'm going to have to do all three of those, which means it's really three little proofs. And let's just have a look at that definition again. Definition says, I'm just going to point something out in this definition. It has 1, 2, 3, 4, 5 moments when we said that something was in the subspace. All of those moments have to happen in our proof. And the only way to for sure say that something is in the subspace is to use the rule for deciding if it's in the set or not. A subspace is a kind of set, and a set has a rule for deciding if something's in the set or not. And so every time that in W happens, you have to use the rule for deciding if something's in your set. So I'm going to make that really explicit here. So this is the rule. These things have to happen in order for something to be in this set or not. And it is still a set, even though it's a subspace. A subspace is a special kind of set. So the first thing I need to do is to provide some arguments and then say, therefore, the zero vector is in this set. And the way to tell if any vector is in the set is to sub its coordinates into this equation to see if they work. So 0 minus 0 is 0. And 0 plus 3 times 0 plus 0 is 0. Therefore, since it satisfies the rule, it's in the set. Okay, so that's part one. Part two of this first way is, now how does the rule go? It says that if something is already in the set, then when I multiply it by a scalar, then it's still in the set afterwards. So that means I need to, when a thing that you're trying to prove begins with an if, that means your proof will say suppose, because you're trying to say, well, what if this happens? Then this would happen. So suppose I need a vector that's in there, x, y, z is in the set. And then I need to do some working, and k is a real number. Do some working, blah, blah, blah. Therefore, and then claim, therefore, that k times x, y, z is in the set. That's not z. That's what I need to do. That's what this part of the proof is going to be like. And so both of these need to refer to the rule for deciding if something's in the set. The only way I can know if this is in the set is if I sub it in and it works. So since I've already supposed it's in the set to begin with, I can just say that it works. So therefore x minus y is 0 and z plus 3x plus y is 0. Okay. Now, I need to get to the point where I say that k times this is in the set too. So I'm going to figure out what k times this is. K times x, y, z. I'm going to give this vector a name. Can I call it v? Let v be equal to this. Then k times v is equal to that, which is kx, ky, and kz. And if this was in the set, then it would satisfy the same equations. So let's see. The x coordinate minus the y coordinate. Oh, look at that. If I go bring the k out, I get x minus y, but I already said that x minus y is 0. So that's k times 0, which is 0. And the other equation, k times z is the z coordinate, 3 times k times x plus k times y. I can bring the k out of that as well, z plus 3x plus y. And that's already 0 because I said it was, and so that's 0, 2. And so since these new coordinates satisfy both of the equations, therefore k times v is also in the set. Now, one more rule to go. There was rule 0, which is about the 0 vector, rule 1, which has the scalar multiplication, and rule 2, which was about addition. So let's say that both u and v are in S. Okay, and I'm going to let u be like A, B, C this time, and v be X, Y, Z. Okay, so since they're both in the set, I'm allowed to say that A minus B is 0 and C plus 3A plus B is 0. And also X minus Y is 0. Okay, these are definitely true. And my goal is to say somewhere at the end, therefore, U plus V is in S. And the only way I'm going to be able to do that is to figure out whether its coordinates satisfy these equations, because that's the rule for being in this set. And so I should figure out its coordinates. So U plus V would have coordinates A plus X, B plus Y, C plus Z. And then I have to sub these into the equation to see if they come out to 0. So the X coordinate minus the Y coordinate, well, that's the same as A minus B plus X minus Y. And I just said that both of those were 0, which is 0. And the Z coordinate plus 3 times the X coordinate plus the Y coordinate. Okay, look, I'll have C plus 3A plus B plus Z plus 3X plus Y. They're both 0, and so it comes out to 0. And so therefore its coordinates satisfy the equations, and it's in there, and I can say, so S is a subspace. What do people feel about this proof?
I liked it, David.
Yep.
Thought it was good.
Yeah, spot on, David.
Yep, and
Spot
so
on.
how do you feel about being able to reproduce this sort of thing?
Yeah, I reckon I could do it. I'm pretty
Be
confident.
good. Is it a similar process each thing? You know.
Yep,
Yeah.
every time you prove something to subspace, you have to do that. And
Yeah, okay.
all of those moments have to happen where you reference the rule for being in the set. That's the key that makes this work. So it happens 5 times. Yeah, because it's mentioned 5 times in the definition, so you have to mention it 5 times in the proof. Yeah, and that's the key. Anything that's mentioned in the definition has to be sort of mentioned in the proof. I do want to do another way. I know I've gone over, but I just feel that I want to do this other way, because this is the proof that anything with linear equations is a subspace. So this is my way 2. So X minus Y equals 0 and Z plus 3X plus Y equals 0 is the same as 1 minus 1, 0, 3, 1, 1 times X, Y, Z equals 0, 0. I can rewrite those 2 equations as a matrix. Okay. And so what I'm going to do is let A be this matrix. Because then S is now the set of vectors X, so underline X to represent the whole vector, such that A times X is the 0 vector. So this is just here, A times bold X, underline X is underline 0. And now I've turned it into something that doesn't even reference any of the specific numbers at all. And then I can do the proof actually really quick. So I still have to do the same thing. So I have to do some working that concludes with 0 vector is in the set. So, some working that says now concludes 0 vector is in S. But watch this. To tell if the 0 vector is in there, I'm going to have to see if it satisfies this rule. So A times the 0 vector, well, that's always the 0 vector. And so therefore the 0 vector is in S. So that's law 0. And law 1, well, suppose that V is in S. And then at the end, I have to conclude that K times V is also in S. So K has to be a scalar. Well, if V is in S, then A times V must be 0 because that's the rule for being in this set. Well, let's see what happens when we do A times KV. Well, look at that. The K comes out because that's how scalar multiplication works. And AV was the 0 vector. And so I get 0. And so since when I do A times KV, I get 0, KV must be in the set.
Yeah, that's good, David. I like that.
Suppose both U and V are in S. Well, I need to conclude that U plus V is in S. Well, then let's see. To do this last bit, I'm going to need to figure out what A times U plus V is, do some working and get the 0 as the answer. That's how to tell it's in the set. But these are already in the set, so I know that A times U is 0 and A times V is 0. Well, I can expand it out. AU plus AV, and they're both 0, and so it's 0. This is the proof that any set of homogeneous linear equations always gives you a subspace, because it will be the same every time. If you just make this matrix A represent the linear equations, it'll work. So I kind of like doing it this way because it's the same proof every time. There are some subspace proofs that won't be exactly like this because both of these proofs are based on the, set of things rule version of set. But if your set is defined as a construction, it won't feel the same way. Yeah, I'll do one.
That's a splendid way to go about it, though.
Sorry?
That's a splendid way to go about it, though.
Yeah, thank you.
Wow.
And this is the power of algebra, right? I mean, I say power, and of course, most people, when they say the power of things, it's like solving useful problems that you have in your everyday life. This is not a problem you have in your everyday life, but from an algebra point of view, this is a really cool algebra thing to do. Like the whole point of algebra is to be able to do things without reference specifically to any specific number. So this is like mega meta algebra, right? It's like, oh, this was already algebra, but I've removed all the numbers and replaced them all with letters. And so it's like, yeah, I think it's fun. Anyway. So I'm going to do one more just to show you how this is similar and how it's different when your set is set up as a construction. So let W be the span of 1, 0, 3, and 5 minus 8 half. Prove that W is a subspace. Okay, so I'm still going to have to do all the same things, but it's going to feel different because my set is written differently. This is a construction sort of set. So W is the span of this, which means it's actually S of 1, 0, 3 plus T of 5 minus 8 a half, such that S and T are in R. That's what span means. It's all the linear combinations. So if I want to prove it's a subspace, I have to prove the same things. So I need the 0 vector to be in there. I need to do some working and say, therefore the 0 vector is in W. Well, to show that the 0 vector is in W, I have to show that it's possible to write the 0 vector in this format, which it is, because I can go 0 times 1, 0, 3 plus 0 times 5, 8 a half is, 0, 0, 0, which is the 0 vector. And so therefore the 0 vector is in W because it can be written in this format. See how much harder that is? I can't just sub things in. I have to try and sub the right thing in to make the thing I want. Okay, so now I'm going to suppose that V is in W. Maybe I'll call it W since it is called W. Do some working and conclude, so, and K is a real number, and conclude that KW is also in W. I don't know if I've given my, I'm sorry. It is a bit fuzzy, but I can't make my document camera any clearer. If I go closer, I might be able to. How's that? Sorry, that was just someone was saying they couldn't see it. Okay, I think that's the best I can do. All right, so this means I'm going to have to show that KW can be written in this format, which means that I'm going to need, I don't know, and this means that W can be written in this format. So let's say that, so W is equal to S of 103 plus T of 5 minus 8.5. Okay, that's what it means, for some S and T, because you're not supposed to say what letters, use letters unless you say what they are. Well, then KW would be K times this. Which would be KS times 103 plus KT times 5 minus 8.5. And these are scalar multiples just as much as these are. So it's in the right format to be in the set W, because KS and KT are totally good numbers in R. And then the addition will be similar. So suppose V and W are both in big W, then V will be, well, we already said that W was S of 103 plus T of 5 minus 8.5. Then this one will be like A times 103 plus B times 5 minus 8.5. They don't have to be called S and T, they're just allowed to be letters for A, B, S, and T in R. Well, then see what happens when we do V plus W. I'm going to have to add these together, and this plus this will be A plus S lots of 103, and this will be B plus T lots of 5 minus 8.5. And these are perfectly good real numbers, and so it's in the right format to be in the set. And so W is a subspace. So even though it was similar, we still had to do the same bits and pieces. We had to still do the 3 different parts, and we still had to use the in sign, 5 times, well, 6 technically, 5 times. It felt different because the rule of how to tell if something is in this set is a bit different than it was before. Yeah. Well, I'm going to ask people how they feel one more time, and then I'm going to stop.
Yeah, I like that,
was
David.
Top notch,
Yeah.
David.
Yeah.
Yeah, thanks very much.
Subspaces is my favorite bit.
Squeaky clean, David.
Thank you. So don't forget, the Maths Learning Centre is open virtually. There's a My Uni course specially for it. It's not your Maths 1A course. There's one just for the Maths Learning Centre. You can get to it from our website, and I gave you a link in the email. And there's all the old revision seminars for everything. So, I think last semester, in semester 2 last year, I did trig substitution. So for someone who asked about that, and most of the course is there somewhere if you just have a look around. But also the drop-in centre's open. If you drop in and stick a discussion board post to say, hey, I want to talk about Maths 1A about this topic, and then they'll probably start a Zoom session. And if there's several of you in the virtual discussion board at once, you can all join the same Zoom session with one of the tutors. So we're open. The Zoom sessions are only announced inside the discussion board. So you put a post and then they'll say, hey, I've finished the last one. I'll start a new one with you if you want. Don't forget to refresh. The discussion board doesn't refresh automatically. You have to do it manually. Yeah. So, yeah, just use it. We're open all the way to the Monday to 10 a.m., Monday to Friday, all the way to the end of the exam period. I know that your exam is really early, and that's why I did this today, so that you still had a week to talk to us.
Yeah.
All right.
Yeah.
Thank you for coming, everyone, and thank you especially to the people who used their voice to tell me how they were doing and used the chat to tell me how they were doing. I wish you all the very best for your exam, yeah, good luck. It's a weird ass semester. Yeah.
No, cheers.
Thanks, everyone.
Cheers, David.
Yeah, thanks very much.
Thanks very much.
Thanks.
Thank you, David.
Such a legend.
Amazing
And
stuff.
yeah, it's just a way of explaining it that it doesn't, that just works sometimes.
Thank you.
Yeah, well said.
Took a few years to figure that one out. There will be a recording of this, but it'll be Monday before it's ready.
Right.
Yep.
I had a
Notes will come
question.
out. Sorry.
Oh, did you? Oh, okay, thanks. Yeah, David, I had a quick question. So are you going to do any more of these, and you're going to post them on the?
I don't have time to do any more for
no
Maths
worries.
1A this semester.
But there is past ones that go
all
what?
the past ones there. I've been doing this for like 10 years, so there's
Yeah,
I've
fair enough.
deleted the ones, most of the ones that don't relate to the new version of Maths 1A.
No worries.
And they're organized by topic. So if you go onto the web page,
Yep.
there's a
Okay.
resources page just for Maths 1A.
Yep.
And they're all organized by topic. But you can also just go to our YouTube channel and Google.
Oh, okay.
something.
Yeah, so David, this isn't on the My Uni part. We can get to this on the web page.
Just straight from the Maths Learning Centre webpage.
Yeah. Okay.
Right.
Yeah.
Yeah.
All right.
Okay.
Thanks, David.
Yeah, and that's where this video will go eventually, but I'll also email you all to tell you where it is.
Okay. Cool.
Right. Yeah.
All right. Thanks for your help, David.
Good luck, everyone.
See you later.
Yeah. Could I ask one quick question?
Uh-huh.
Yeah. Is it possible if you could maybe upload your notes or something that you just?
Yes. No, I will scan these on Monday.
Yeah.
And I can't do it till I get back to work on Monday. I'm at home today. But I will scan these notes, and they will go onto the website with the video as well. But
Right. Okay.
yeah, but I'll also just
Okay,
put them in the I'll put them in the email.
Yeah. No worries.
Thank you so much.
You're welcome.
So much.
Woohoo.
See ya.